In this presentation, we're going to try to put together everything that we've learned so far about setting up problems to actually solve some of these word problems. Some of these problems that we will work with are about the same as what we will see in our online homework and textbook problems, and some of them may be a little bit more intense, but it's good to see some of the more intense problems and see how this can be extended to that. In the last lecture, we talked about how to set up conversion factors and find basic starting point numbers, so to tabulate our data in a useful way. So we're going to put that to work. We're going to use something called factor label method or unit cancellation method for solving our problems. And basically, if you've taken a math class where you've dealt with fractions, there's a way that you can simplify the fraction. So in the first number here, I've got 2/3 times 1/2, and we can simplify this by canceling the 2's. I've got a 2 in the numerator and I've got a 2 in the denominator. Perhaps you've even went so far as to multiply algebraic expressions that were ratios. So in this second one, we've got an x in the denominator and I've got an x in the numerator. So I can cancel those out. So in the first one, I guess if I cancel the 2's, the answer to that first problem is 1/3. If I canceled the x's in my second problem, my answer would be 4/3. We're going to do the same with units. So if I had something like 5 centimeters per minute and I was interested in how many inches per hour that corresponded to, then I can convert my centimeters to inches and I can convert my minutes to hours by applying the ratios in the right way. So since my centimeters is in the numerator, I wanted a conversion factor where centimeters was in the denominator of the next cell. And then whatever it is equivalent to has to go in the numerator of that cell. So I can get rid of my centimeters in that case. And then I moved on to handling minutes. So I have minutes in the denominator of my starting point, and I need to get rid of those minutes and get into hours. So I needed to express that relationship with minutes on top and hours on the bottom. And whatever relationship I have has to be true. There are 60 minutes in 1 hour, so the 60 has to go with minutes and the 1 has to go with hour. I didn't actually work this one out. I just kind of randomly put this together, so that looks like it's about 300 divided by almost 3. So the answer is going to be a little bit more than 100 here, so I'll let you do that on your own. It wasn't important. It was just more to explain how we're going to go about our math. Okay, so remember the slides where we set them up. Here's our setups, and I said in the last presentation that usually the number that has the simplest unit, so it's not a stacked unit, stones per hour or whatever, there are stones per something. So I want to start with something that is a direct measurement. So somebody stepped on the scale and it read 8.65 stones. That's my starting point. Anything that is an equality is going to be a conversion factor. So when I actually work through this problem, I'm going to start out with 8.65 stones. And I usually work these rather than having a set of fractions. I usually use what I call railroad tracks here. So I'm going to have a horizontal line, and each factor I apply is going to go in a successive cell. So I'm starting out with stones in the upper left-hand corner. So I almost always go to that upper left-hand corner. There's nothing typically below that unless we're converting a conversion factor. But if you're uncomfortable having an empty cell there, you can always occupy it with 1, because anytime you divide something by 1, you don't change it. Okay, so I've got 8.65 stones to start with. That means in the denominator, the downstairs portion of the next cell, I've got to have stones there. And I've set up my conversion factors, and it looks like the right-hand one, the 14 pounds over 1 stone, is what I need to be using there. So I'm going to plug that second conversion factor in there, and I've got 14 pounds over 1 stone. And if I actually process that through my calculator, I'm expecting to report my result to 2 significant figures, possibly 1 significant figure. This is a problem that's not very well written because that conversion factor for stones to pounds I'm not sure whether there's one or there's two significant figures there. But anyways, I reported it to two significant figures. I'm not that terribly picky on this. So 120 pounds would be roughly equivalent to 8.65 stones. Okay, moving on to this problem about the caffeine and the coffee. 2 cups of coffee, it's a simple unit. It's not directly related to anything. They don't tell you that 2 cups is equal to something else. So that's going to be where I suspect my starting point is. I've got other relationships here. 1 cup is 6 ounces, so that looks like I can use that one next, and I've got a couple of ratios there. And since cups is in the numerator to start with, I want to put cups in the denominator in that next cell. So I've got 6 ounces over 1 cup. We also know that 6 ounces is equal to 105 milligrams of caffeine, so I can use the second form of that equality, so 105 milligrams over 6 ounces of coffee, because I want to get rid of my ounces of coffee next. So now the units have canceled for ounces of coffee, and I've gotten rid of cups of coffee. The only units that have survived cancellation at this point are milligrams of caffeine that are in that coffee. So we ultimately want to relate the milligrams of caffeine to ounces of chocolate. So I've got another relationship here that relates milligrams of caffeine and ounces of chocolate. And it looks like I'm going to want my milligrams of caffeine in the denominator, because currently I have milligrams of caffeine in the numerator. So it looks like of my two relationships here, it looks like I should be using the first of the two, chocolate milligram of caffeine relationship there. So I can plug that in, and once I plug all my numbers through, it looks like the best answer here would probably give me 2 significant figures in my answers. We've got a few measurements that are made to 2 sig figs in this. So if you want to have the same amount of caffeine that you would from 2 cups of coffee, then you could consume 14 ounces of chocolate, at least according to the data given in this problem. Okay, the chloroform problem. The starting point would be the 9.37 grams of chloroform. It's a direct measurement. It's not a compound measurement like the density is. So I've got grams of chloroform, and the density is a relationship between grams and milliliters. So it looks like I want to get rid of grams, so I want to put my grams on the bottom and milliliters on the top, so it's going to be the second form of the relationship. And the equivalent amount of chloroform in milliliters would be 6.32 milliliters. I went with 3 sig figs here because my initial measurement had 3 sig figs, the density had 4. So I always go with the fewest number of sig figs. Okay, the Hope Diamond problem here. So I've got all the information. The simplest units are the 44.4 carats. That's going to be my starting point of that calculation, and I need something next that is going to relate carats to something else, and it looks like carats are related to milligrams. So I want to have 200 milligrams over 1 carat. And so I'm all out of carats, and I want to be into milligrams at this point. And it looks like another relationship that I wrote down was the relationship between milligrams and grams. So I'm going to go for it there. I see that there's a typo here. My second form there of the milligram-gram relationship should be that there are 1 gram over 1,000 milligrams. I think I got it right in my kind of animated slide here, and I do. 1 gram is equal to 1,000 milligrams. So now I'm in grams. Ultimately, we want to know our mass in ounces. I'm going to get out of grams because I know that I have a relationship between grams and ounces, and I know that I want to use the 1 ounce over 28.35 grams relationship. So if I plug all my numbers through my calculator, and I forgot to mention how we do this, basically I multiply it all the way across the top, so 44.4 times 200 times 1, or you can skip that step because really it doesn't accomplish anything, times 1 again. Then I'm going to divide by 1, then divide by 1,000, then divide by 28.35 grams. And if you do that in that order, you should end up getting 0.313 ounces. The other diamond problem, I think I just rapidly went through this. We're going to start with the same starting point, the 44.4 carats, and use the conversion factors that we have already defined in problem 119, along with problem 120 here, that define the relationship between grams of carbon and numbers of carbon atoms, as well as the density. So I kind of worked these out here. I started with 44 carats, as I said, in each place. I'm going to convert those to milligrams and then to grams. So the first 3 steps are the same for both problems. And then in finding out the volume in centimeters cube, let's see, it says what is the volume, so it doesn't tell us what unit, so centimeters cube is usually where I'm going to stop here. So I use the density in the first problem, and then the second problem I use the relationship between atoms and grams. Okay, here's our irregular chunk of silicon. We've already just directly measured the mass and the volume, and like I said, sometimes it's just easy to start with the formula. So my starting point for this is going to be my density formula, and if I just plug the mass that I measured in on the top, because I want grams over milliliters, that's literally what grams per milliliter mean. I can take my 8.763 grams and divide by 3.76 milliliters, and I get 2.33 grams per milliliter. As it turns out, a milliliter is the same thing as a cubic centimeter, so we also could write it as 2.33 grams per centimeter cube. Typically, if we're talking about solids, we're going to talk about grams per centimeter cube. If we're talking about something that's a liquid that we can actually use as a volume measurement that we'd measure with a beaker or a graduated cylinder, then we're going to use milliliters more often than not. Okay, the problem about the amount of the digitalis that a 160-pound person ought to receive as a dose. I said before that we'd probably start with the 160 pounds because that's my simplest direct. Okay, here's the digitalis dosage problem, and I mentioned that we'd start with the simplest unit. The simplest unit is the mass or the weight of the patient, so 160 pounds. We've got to turn that into kilograms because the dosage is based on kilograms, so I'm going to take the 2.2 pounds per kilogram, so I'm going to arrange it so that the pounds cancel, leaving me with kilograms, and the dosage says that for every 1 kilogram of body mass that the patient can have 20 micrograms of the medicine, and for some reason we want the dosage listed in milligrams, so I'm going to get rid of my micrograms, and to do that I could compare it directly to milligrams, but I more often than not make a mistake, so I always compare it to the base unit first. I know that there are 1 times 10 to the 6 micrograms per gram, and then I can turn the grams back into milligrams. And then when I plug all the numbers through, I multiply through the top, divide by the bottom, and it looks like this patient ought to have 1.5 milligrams of this digitalis. Slides here. I think I got the next one right. So I've got my starting point of 171 kilocals, and if I start out with 171 kilocals, 1 kcal is 1,000 cals. 1 calorie is the same as 4.18 joules. 1,000 joules is a kilojoule. 17.9 kilojoules correspond to 1 gram of sodium. I just went there because it first asked for the amount of sodium, so I went with the amount of sodium. Once I found this, sometimes once you have solved a problem, you can use that answer as your starting point for the next question. So it asked how many sodium and then how much chlorine could be made. So I know that I can relate the amount of sodium to the amount of chlorine. So 39.9 grams of sodium is my starting point, and 1 gram of sodium corresponds to 1.54 grams of chlorine. So I can just calculate that directly.